Alright, continuing my point 3 lesson, which is improper integrals. We're going to get to the point where you can use the direct comparison test or the limit comparison test. So the direct comparison test, well, I'm going to use that in the first example here. But if you're trying to determine whether an integral converges or diverges, the first thing you want to do is try to find the antiderivative. And we can't find the antiderivative of sine x over x cubed, at least not easily, so I don't know what it is. So what we can use is the direct comparison test. So the direct comparison test, if we have an integral, and let's say I've got this integral, this is some f of g. If I want to integrate or find the area underneath the curve of f of g from 1 to infinity or whatever, if I know that this one converges, if f of g converges and it is bigger than g of x, so if f of x is bigger than g of x, and I know that f of x converges, then g of x must converge. So if I know that some integral above it is going to converge, that means we can figure out what the number is. Then certainly a function, as long as it's always below f of x, that also is going to come up with a number, because it's going to be smaller than that one, and this one does get a number, not infinity, so then this one would be convergent also. So that's one statement that you can make with the direct comparison test. If you're trying to figure out if g of x converges, and you can find a function that is bigger than that, and you know that one converges, then you can say that this one converges. So the other statement is, if g of x diverges, and you're trying to figure out if f of x diverges, well, if this one goes to infinity, then certainly anything bigger than it will also go to infinity. So if g of x diverges, then f of x diverges, because it's bigger than g of x. So you're comparing two different functions. It doesn't work. So if I know that g of x converges, I don't know if f of x converges. So if this one produces a number, I don't know if that one does. If f of x diverges, well, I don't know if g of x diverges or converges. So it's not the end-all type of a problem, but there are two statements that can be made. If this one converges, then this one will. If this one diverges, then that will diverge. So in this problem, and they're often with sine x or cosine x, that's pretty common for a direct comparison test. So if you see like a sine x or a cosine involved, a lot of times that's an indicator that you'll use the direct comparison test. We know this about sine x, that it is always between -1 and 1. So the biggest sine x could ever be is 1. So the expression sine x over x cubed is always going to be less than or equal to 1 over x cubed. The biggest it could ever be is 1, so it's going to be less than or equal to this one. So now we need to know about the integral of 1 over x cubed from 1 to infinity. So what do we know about that integral? Well, we can find the antiderivative. That's x to the -3, so x, we're going from 1 to b as b goes to infinity. So it's -1 over 2x squared. If I plug infinity, I get 0 minus. If I plug in 1, I get -1/2. So 0 minus -1/2 gives me 1/2. So since I got a number, Therefore, the integral 1 over x cubed from 1 to infinity converges. And that's the bigger of the two. If the bigger of the two converges, this would be the 1 over x cubed. It's bigger than that. And this one converges, then the smaller one must also converge. So then you would safely say that sine the integral from 1 to infinity of sine x over x cubed dx converges using the direct comparison test. So there's a couple things you need for the direct comparison test. You need a function to compare it to, or an expression to compare it to. That's not always easy to find. You also need to know that if the function you choose, if that one converges and it's bigger, then you can safely conclude that the smaller one, or the original, converges. If what you are comparing it to is bigger and it diverges, it doesn't do you any good. We can't. So if this integral right here had diverged, we just wasted our time, because the bigger one diverged. Great, we don't know about the smaller one. So the logic sometimes can be confusing. The expression you compare it to isn't always easy to find, and it doesn't always work out because it might diverge when it's bigger, and so on. Okay, so in conclusion, sometimes you have to use the direct comparison test. Like this one would require the direct comparison test, but it's better to use the limit comparison test because the logic doesn't have to be as specific. Test, use it only when you have to. The limit comparison test is what you should try first. Notice when we do these tests that we did not figure out what this integral actually is. We don't know what the integral of that from 1 to infinity is. We can only state that it converges. You'd have to use your calculator, I guess, to approximate that integral. We aren't figuring out what it is, it's just that it converges. Alright, so limit comparison test. Limit comparison test. Alright, so if you have a function, let's say we're integrating 1 over 1 plus x squared dx from 1 to infinity. If you compare that to something really close to it, and let's say the original is f of x, and we pick a g of x to compare it to, and if we find the limit as x goes to infinity, if that gives you some number L or some finite number, that means that they grow at the same rate. So if they grow at the same rate, then you would say that they behave the same. So I guess if the limit of the one over the other is some number, they behave the same. So in other words, they both converge or both diverge. Okay, we don't need to know which one is bigger than the other one. We don't have to use a whole bunch of logic. We just have to find an expression or a function that is really similar and it grows at the same rate. Well, if you think of our end behavior here, our end behavior model of 1 over 1 plus x squared, this 1 is so small that it really doesn't play a part in as x goes to infinity. So it really behaves the same as 1 over x squared. Okay, so these two are pretty darn close to each other. They basically become the same thing as x goes to infinity. So I'm going to choose that as my g of x. So now I'm going to find the limit of the original over my comparison function as x goes to infinity. And evaluating that limit, that's the same as x squared over 1 plus x squared. You can see that it's going to become 1. You could use L'Hopital's. I multiply the top and bottom by x squared is what I did there, or just flip this and multiply. So you can see the ratio of the coefficients is 1 over 1. You get 1, you can use L'Hopital's, but our limit ends up becoming 1. And since that is just a finite number, then they behave the same. Okay, so we know that our function, or our integral here, is going to behave the same as this integral, 1 over x squared dx from 1 to infinity. We know they're going to behave the same. So now we need to know what this one does. Well, we can find integral of x to the negative 2 from 1 to infinity. Antiderivative of that is x to the negative 1 negative from 1 to infinity. So it's negative 1 over x from 1 to b as b goes to infinity. So I get 0 because I plug infinity and I get negative 1 over infinity 0, minus plugging in 1 I get negative 1 over 1, which is negative 1. So we get 1 for an answer. So that one converges. This one converges. So since we got our number here, then they behave the same. So our original integral, 1 over 1 plus x squared dx, converges. I should write converges. This is the comparison. Converges through the limit comparison test. Okay, so it's better because we could, this could, our g of x, we don't need to know if that one is bigger or smaller than 1 over 1 plus x squared. Because I could put g of x on top and f of x on the, you know, if we had gotten 2 for an answer, upside down we would have gotten 1/2. As long as it's a number, they behave the same. So limit comparison test is more useful. So that's what I tried before the direct comparison test. Now there's a shortcut that I have a hard time finding in the book. I don't know if it's in there at this point, but I'm going to tell you right now it's going to be very useful. It's called the p-test. Sounds like you need to pee in a cup or something. But p-test, if we integrate 1 over x to the p dx from 1 to infinity, or 2 to infinity, or just a constant to infinity, this right here will converge if p is greater than 1. So if I have 1 over x squared, or if I have 1 over x cubed, or if I have 1 over x to the 3/2, as long as that p is greater than 1, it's going to converge. And you don't have to explain. You could just say p, like if I had this problem right here, and I was trying to determine whether this converges, I'd say p equals 2, and p is greater than 1, therefore it converges. We had another one here on the previous problem. This one also converges because p is 3, which is greater than 1. Okay, so you can use the p-test all the time in my class. It's really useful. As long as p is greater than 1, it converges. Also, if p is, well, it's implied that p is positive, but if p is less than or equal to 1, and greater than 0. If that's the case, then it diverges. So we know immediately whether it converges or diverges based on what p is. So if it was 1 over x, that means 1 over x would be x to the first, that would diverge. If it was 1 over x to the 1/2, then it would diverge. So if that p is between 0 and 1, including 1, then it will always diverge. So that's the p-test. Alright, let's see. I'll just finish off with the notes. No, not that one. Turn the page. So there's a bunch of integrals in this section. I'm just showing you this one, and it's only one. There's lots of different types of integrals that you can ask questions on as they come up. But if we're given this, the first thing you would maybe think of is a u substitution, where u is 4 minus x squared. Then the derivative is negative 2x. So that x would kind of disappear. But we have that plus 3, so that messes things up. So what you'd have to do is separate the two integrals. Make it x over that and then 3 over that. So you'd have two different integrals by dividing up the fraction. Then you can do your u substitution on the left. And on the right, u substitution, on the right, you could identify that as an inverse trig function, because you have square roots and you've got x's being squared and numbers being squared. Your u is always the square root of the x stuff over the square root of the constant. So the square root of x squared, so x over 2, that's your u. And it is a u substitution, but it's just a different one. And this is the one where you have to solve for x here. So x multiplied by 2 is 2u. So then you could replace your x with 2u in the problem, and you end up getting, after you pull out a square root of 4 on the bottom, which is 2, you end up getting the integral of 3 times the integral of 1 over square root of 1 minus u squared. Let's see if that continues. Which is inverse u. So 3 inverse u, and then you go back and you, it's hard to do here. And u was x over 2, then you can evaluate it. Remember, the inverse sine of 1/2 is asking you what angle has a sine of 1/2, and that's 30 degrees or pi over 6. What angle has a sine of, when you plug 0 in, of 0, and that would be 0. So you end up getting pi over 2 in that half. There's the left half, which is u substitution, so total we get that. This is just another example of a inverse trig. Looks like an inverse tangent based on what we get, x squared plus 9. So your u is the square root of the x stuff over the square root of the constant, so it's x over 3. Solve for x, that's 3u. Solve for dx. Write it all in terms of u, even replacing your x with your 3u. And you have a 9 you could pull out on the bottom, which becomes 3/9 or 1/3, and then it's just inverse tangent. And then our u is x over 3. Some other things I pulled from another book, different techniques that you could use in trying to figure out integrals. Now that's not everything in this section. I really strongly encourage you to get through as much of them as possible, ask questions. I did provide my work, but I'm happy to do more YouTube videos if needed.